This discussion is entitled Touch the Sun, NASA's first mission to our star. And it's a conversation about NASA's Parker Solar Probe. So please welcome from the Johns Hopkins Applied Research Laboratory, Johns Hopkins Applied Physics Laboratory, Betsy Congdon, lead engineer for thermal protection system for Parker Solar Probe, and Nikki Fox, project scientist for Parker Solar Probe.
Thank you very much. Well, good morning, and thank you very much for joining us. Thank you to Monica for the introduction. As she said, I am the project scientist. I have the great honor of being the project scientist for NASA's first mission to go up and touch the sun, which I lovingly call the coolest, hottest mission under the sun. And I hope by the end of this, you will also agree with me just how cool this mission is. But before I get into all of the innovation and all of the really cool technology that Betsy and I are going to share with you today, it's also a mission that's really steeped in history. So I want to take you back to 1958. So in 1958, the space industry was just kind of starting. Up here you see on the left, John Simpson, on the right, the very famous James Van Allen. And it was shortly after James Van Allen had launched Explorer 1, actually 60 years ago in January. And they were asked to put together a committee to kind of come up with all these really cool ideas, and they were asked to provide guidance and advice to the newly forming agencies, so to NASA, the National Science Foundation, and the DoD also. What do we do with this newfound thing called space? What are these really big missions that we need a big infrastructure to be able to do? And so they came up with 12 missions. Of those 12, 11 have already flown. The only one that hasn't flown yet is a probe to go up into the sun's atmosphere. And so why was that proposed? Why are we called Parker? So let's look at Gene Parker. Also in 1958, Gene, then a young researcher, published a paper. He likes to tell me, all I did was publish a paper. But he published this amazing paper, and it led to scientists really wanting to study what was going on close to the sun. So it's also historic because this is the first time NASA has ever named a mission after somebody during their own lifetime. So lots of history in this mission. But if we look at the sun, when you go very close to the sun, we know that the sun's surface is at about 6,000 degrees centigrade. If we we compare that with the corona, that hazy atmosphere that you see during an eclipse, and some of you may have been lucky enough to see the eclipse across America last year. The corona itself is about 300 times hotter than the surface of the sun, so it gets up to temperatures of about 3 million degrees. And that just doesn't make sense. You have a heat source, and it gets hotter as you move away. You know, it's like walking away from a campfire and suddenly getting hotter. It breaks the laws of nature, it breaks the laws of physics. The other thing that happens in this really critical region is that the plasma, or this coronal material that's sort of suspended out there, and you can see a little bit of it in this beautiful eclipse image, it gets incredibly energized, so much so that it actually takes off and can break away from the huge pull of the sun with so much energy that it can move out and it bathes all of the planets. It carries with it the sun's magnetic field. That's very important to us here on Earth because we have our own magnetic kind of bubble in the solar wind, and that was what Gene had postulated and discovered with his paper, was this solar wind. We live in the atmosphere of the sun, so when the sun sneezes, the Earth will catch a cold. We feel whatever is going on the sun. And so it's very important to us because we are very reliant on technology. Again, history, but back in 1859, a young researcher, British astronomer, James Carrington, was looking at the sun and sketching sunspots. And as he was doing that, he saw bright flashes of light, which turned out to be a big solar flare. Just a few hours later, the compass needles at Earth began to spin. The aurora, the northern and southern lights, were seen close to the equator, and sparks flew from the telegraph system, and the whole telegraph system went down for 4 days in the US. Now that doesn't sound too frightening, but try telling your kids they're not going to have the internet for 4 days. And that's exactly why we are more and more reliant on technology, and it's more and more important that we fully understand the sun and the dynamics and what is going on around them. So let's take a look at the mission. So we're answering these two questions. Now, how are we going to do it? So we start our journey on a Delta IV Heavy, which is the largest vehicle that NASA currently has in their arsenal. We will launch from Cape Canaveral. Our launch window opens July 31st. Lost my mic? Oh, there I am. Okay, and so we lift off from the pad, and here we see, so Solar Probe will get her first taste of space. We open the fairing, and out she comes. We lift off the second stage of the rocket, and then even being on a Delta IV Heavy with all this amazing lift mass, we still have an upper stage, and so we blast off even faster away from the Earth. It's important to us that we lose all of the influence of the Earth so we can study the sun. First thing we do is pop out our solar panels to get some power. Out comes one of our deployables. We have things that are stowed when we launch for safety, and we pop those out. You saw, first of all, the magnetometers on the back, and then the radio antennas. Our first stop, just 6 weeks after launch, is at the planet Venus. And we fly past there, and we use Venus to give us a little kick. It's kind of like doing a small handbrake turn in the car. We actually use it to turn us away from the orbit of the Earth and move in towards the sun. And so that's what we do, and just 6 weeks after flying past Venus, we will enter the corona for the very first time. Just notice, Betsy's going to talk more about it, but those solar panels tuck in as we get closer and closer to the sun to protect them. At closest approach, Solar Probe will be seeing about 478 suns, so 478 times the amount of sun we see here on Earth. We are also moving at incredible speeds. Obviously, we don't want to be pulled into the sun, so we have to move very fast to be able to kind of surf around the corona. Just like a surfer surfs on a wave, we'll surf around the corona and not get pulled in. Our maximum speed is about 430,000 miles an hour, or 118 miles a second. I still can't believe that number, but that's what we're going to be doing. You'll notice out the front, our heat shield. The object of the game is to keep our heat shield between us and the sun at all times. And so that has a lot of challenges, just to be able to do all that kind of maneuvering. And it takes light 8 minutes to get from the sun to the Earth. So there is no way, moving at those kind of speeds, that we can possibly sort of joystick the spacecraft from Earth. She is the most independent spacecraft ever to fly. She has so much autonomy, so if something goes wrong, anything happens, she has to fix it herself. So we have little solar limb cells that look around the body of the spacecraft. None of them should ever see the sun. The moment one of them does, the spacecraft is fully coded to be able to correct that error. We're also going closer, obviously, than anything has ever been before. At closest approach, we're at about 3.9 million miles away from the solar surface. And I realize that 3.9 million miles doesn't sound that close. It's kind of a big number. But if I put the Earth and the sun 1 meter apart, Parker Solar Probe would be 4 centimeters away from the sun. So we're going close. We're also, so we're fastest, we're hottest, and we're closest. We will be living, or we will be orbiting through the 3 million degree plasma region. Now, that again sounds really hot, but the plasma there is not very dense, and so if you imagine turning your oven on to like 400 degrees and letting it heat up, you can put your hand inside that oven. It won't burn you unless you touch something. So there's a difference in temperature and heat. And so there aren't that many particles around, so the actual amount that couples into the front side of our heat shield it means that the front side is at about 2,500 degrees Fahrenheit or 1,400 degrees centigrade. Most of our instruments bask lovingly behind the heat shield and are at a temperature just a little hotter than you are right now. And Betsy is responsible for what we lovingly call the 8-foot frisbee, the heat shield on the front. And so let's take a look at some of the features of the spacecraft. So proudly, out and proud at the front, the thermal protection system, the heat shield. Betsy will refer to it as the TPS. Whenever she says TPS, just think heat shield. That is our #1 technology development for the mission. The solar wings on the side there, I mentioned that they tuck in and they come out. That was another huge innovation for us because we had to find a way to cool them. There have been many, many incarnations of a solar probe mission since the 1958 timeframe. And most of them have been kind of cone-shaped, and they've used Jupiter, and they've had some kind of RTG or some kind of nuclear propulsion. In the mid-2000s, NASA gave the Applied Physics Lab a challenge to come up with a new mission that did not require any kind of RTGs, that would use solar cells, and that was considerably cheaper than all of the other missions that had been proposed at the time. And so you may wonder, well, golly, solar power, you're going to the sun. No problem, except there's too much power. So I mentioned 478 suns. And by the way, the solar probe, the sun will be about this big to solar probe. That's how close she's going to be. And so we have to find a way to cool those solar panels and keep them safe. Just looking at a couple of instruments, I mentioned that most of them are on the bus, or what we call the main body of the spacecraft, that is that sort of hexagonal structure at the back. But there are some brave instruments that peep out and actually are out in the environment. And one of them is the electric field antennas. You notice those 4 radio antennas. They are as far away from the spacecraft as we can put them because we want them to measure all the excitement in the solar wind, not what's going on in the spacecraft. So we have those out as far as possible. The one I always think of as the bravest little instrument on the spacecraft, you see at the top there, SWEEP SPC. That is the solar probe cup. It's a simple Faraday cup, but it's a simple Faraday cup that has to survive these huge temperatures. And one of the things I didn't mention is our orbit is highly elliptical. We go very close to the sun on one side, and then we come out around the orbit of Venus on the other. And so we can continually use the planet Venus to do a little bit more handbrake turning, and so that we can come in closer and closer to the sun each time we encounter the planet Venus, and we do that 7 times. And so these instruments, not only do they have to withstand incredible heat, and indeed the heat shield is the same, but they have to survive hot, then cold, and hot, then cold. Dramatic heat changes 24 times for our prime mission. You think of taking any material and heating it and cooling it, it becomes brittle and its properties change pretty quickly. And so huge, huge technology innovation to be able to come up with these materials. And Betsy's going to tell you a lot more about those. The PI, our principal investigator for these instruments, Justin Casper at the University of Michigan. And if we flip the spacecraft over so you can see the other side, you will see most of the instruments now that are on the main body of the spacecraft. I'll quickly go through them. WISPR is a white light imager. It's going to be taking fairly unusual pictures. It's not going to be taking the big suns like you saw with that SDO image that I showed earlier. It's going to be literally taking pictures of what the spacecraft is about to fly through. It's a very unusual imager, and it's going to help us to unpack the data. If you imagine, we're moving at about half the speed of the solar wind. And so as we're going towards the sun, we're kind of, hitting up against the solar wind, and all those features are going to become very, very narrow. When we come out, we're moving away. We're now moving in the same direction, so everything is going to get smeared out. And being able to just do the comparison and find out what is going on in the solar wind, this imager is going to be invaluable to us. Also highlight the ESIS suite. That's our energetic particle detectors. And they're measuring the high energy guys that are associated with flares, with shocks, with coronal mass ejections that we all hear about in the news, where we worry about what's going to happen to our technology here at Earth. And if you imagine, we've got this sort of bulk property, a bit like a river flowing downstream, and on top you have a motorboat that's going really fast. There are high energy particles. Measuring the bulk, this sort of ever-flowing solar wind, is the SWEEP suite, which is very hard to say. We have one detector on this side of the spacecraft, one was on the other. Together their fields of view fit like a baseball, and so it gives us a full 360-degree view of what's going on. Last but certainly not least, at the very back here, we have our magnetometers. Again, we have those on a long boom so that we are measuring what is going on in the solar wind, not what is going on in the spacecraft. Because you can imagine there's a lot of currents and things flowing in wires on the spacecraft, and I don't want to know what the spacecraft's doing. I really want to know what's going on in the solar wind. And so I'll leave you with the question of why has it taken us 60 years? You know, it's been the top priority mission in all these decadal surveys that the National Academy do. It's been the top priority mission for NASA for such a long time. But we've had to wait 60 years kind of for technology to catch up with our dreams. I heard a great quote the other day that it was at an engineering festival, but that scientists see the world as it is, and engineers see the world as it could be. I tried not to take that personally. And I said, you know, with this mission, it really is scientists and engineers working hand in hand. The scientists envisaged a mission that we desperately wanted to do, and it took a while for the technology to be able to catch up to what we need. Just the sheer scale of the autonomy system that I talked about, the amount of coding, the amount of, we call it fault management. So something happens on the spacecraft, a fault, the spacecraft has to manage itself. The coding that would have been necessary to do that in 1958, I don't even know, it would have been 7 city blocks worth of buildings just to house that computing. You know, you think 1958, you wanted to make a phone call, you had a rotary dial phone. It was attached to a wall. A mobile phone meant that you had a longer cord and you might actually make it to the living room and not have to stay in the kitchen. Now we all have iPhone 8, X's, whatever, Samsungs. You use it for practically everything than making a phone call. But if you think of just the amount of electronics that you hold in your hand and compare that to what was available in 1958, they are the huge leaps in technology and the huge amount of innovation that we've had to wait for to be able to do this mission. And so without further ado, I will introduce Betsy, who is going to tell you about these amazing innovations. And she's also the heat shield diva, so she's good.
Thank you, Nikki. So yes, I'm Betsy Congdon, and I'm the lead engineer for the thermal protection system, which is our fancy way of saying heat shield. And I will refer to it as the TPS a lot, and as Nikki already said, so bear with me. I'm up here representing the hundreds of engineers that have worked to innovate and figure out how to make this mission possible and make those science dreams come true and understand these mysteries at the sun. So let's start off just quickly. I'm going to walk down the spacecraft. I know Nikki has done this, but we look at the spacecraft all the time. We know what all these words mean, so we'll emphasize it. So up at the top, near the word probe. So anyway, we don't have the video. We don't have the picture I was just about to talk to, but I will. I'll just talk a little bit about. So we've got the heat shield out front. Right behind it, we have those corrugated-looking black pieces, and that is the radiator for the cooling system, which Nikki mentioned, and I'll talk a little bit more about. And then behind it, we have the spacecraft bus. That's that hexagonal shape that has almost all of the stuff, besides the few instruments that are up at the top and the heat shield. The effort it takes to actually build up this spacecraft not only is about the innovative parts I'm going to be talking about, but it takes lots of time and effort and human energy to actually put it all together. So all of the various components have been built up for many years. I've actually been working on the job for 10 years, starting with just a piece of paper. We think this is what a heat shield looks like, building up into an actual heat shield, which you'll get to see today. Many of us have been working on it for a very long time. In fact, just putting the pieces together, a process called integration and test, or INT, started in July 2016. That's where we actually start assembling things, and it actually starts looking like a spacecraft. So let's start that journey with Solar Probe. So the very first thing that happens is we have that primary structure, that bus, come together, the honeycomb hexagonal panels. And then we add the harness. This is how most of the boxes are going to talk to each other. You can see there's a lot of harness on this spacecraft. And then we get our first innovative feature that's very important, the cooling system. You'll see this referred to as the SACS as well, Solar Array Cooling System. We do love our acronyms. And it's actually integrated in the top deck of that hexagonal structure. And so you can see they're taking off a dummy top deck there, and they're going to bring in the radiators that are sitting on the actual top deck, as you see coming over. You see the red wings are sticking out. Those are not on there for flight. They're actually holding up the tubing that's going to actually connect to the solar rays. So this cooling system works a lot like the veins and the arteries in your hands. The water flows through the solar arrays and heats up. Nikki mentioned that we are solar power, but we have too much power, too much energy, because as you get close to the sun, things get hot, and solar cells do not like to get hot. They can become less efficient. So we have this cooling system that's designed to actually pull heat away from the solar cells to keep them in a very happy place. So we have the power we need. Pull that water through the radiators that you see up there, the black corrugated features, which see outer space, so they cool off. So we kind of have a heat exchange going on. You might also think water, that's a unique, it's not very interesting of a liquid, but they actually went through and looked at what the best liquid would be, and water is a great material, and it's why it's so vital for us to be here on Earth. And so it actually worked very well to actually be in the cooling system, and it was determined to be the best liquid for that purpose. So next we've got the high gain going on. The high gain is really important because it's actually how we talk to Earth and bring down the data from Earth, the science data. And now we have the solar rays. So the solar rays themselves are also a very important innovation that was critical to this mission happening. Here we've got a pause shot. They're actually putting on one of the wings. There's 2 wings on either side. And you saw the video where they actually popped out when we are far away from the sun, and they pull in when we're close to the sun. Same reasons that we need the cooling system. As we get close to the sun, they get hot. They're less efficient when they're hot, so that's why we actually actuate the solar rays throughout the mission. Here we have one going on. And you can see on the right-hand side, there's a cover. We like to keep the actual solar cells themselves protected. The solar cells were a very critical innovation that was developed in order to enable this mission. Solar cells here on Earth are obviously different than solar cells we might use on a mission that's going around the Earth or going to the moon. And neither of them work very well for actually going to the sun. So a lot of work went into how do you actually make a solar cell that's going to work at the sun, and then how do you integrate it into that cooling system so that you can pull heat away as you need to. So let's continue on. Once we have the solar cells on, or the solar arrays on, we're almost done. Most of the bus is there. And so we start putting on instruments. Here is EPI-Low. It's one of the instruments that Nikki talked about. And you build up an instrument, they test it, we do all sorts of things before we actually put it on the spacecraft, and then we do that all over again. And that's one of the reasons why it takes so long. We make sure that everything works. And then we have a whole system. We're going to pause here. This is the exciting moment right before release, you know. So we have a whole system, and at this point in time, we have basically everything on there except for the heat shield, which I'll talk about a little later. So the heat shield obviously sees a different environment than the rest of the spacecraft. Nikki mentioned the front side of the heat shield at about 2,500 degrees Fahrenheit, but the spacecraft bus is only a little hotter than room temperature. And so we actually test those components separately to make sure that we know that they're going to work in the environments that they are going to see. And so you're going to see that a little bit. One of the first system tests that we do on the spacecraft is the magnetic swing test. And that's what you're about to see in action. Nikki said that obviously we're going to the sun to understand what's going on there magnetically. But the spacecraft has currents, it has a magnetic background. And so this swing test is actually where we test what the magnetic background of the spacecraft is so that the scientists can use that to take their data. So let's roll that. I know it doesn't look that exciting, but it is really exciting for us. It's like it's flying around. So next we get into environmental testing. So we've got this spacecraft together, and here we see it being loaded into a chamber. We can pause right here. It's about to go into the chamber which you see below at Goddard. So spacecraft environmental testing is where we say we've got the whole thing together, let's put it through its paces and make sure it's going to survive launch, it's going to survive all that thermal cycling that Nikki's talked about. So the first thing we do is we actually take the spacecraft and we put it through acoustics and vibration testing, which simulate launch. We make sure everything works before and after and everything is good. And next, we go into thermal testing, which is what this video is going to show. So you can start that up again. You can see it's bagged so that we don't have any contamination concerns as we come into the chamber. This is also exciting. So we put everything in. I mentioned the TPS isn't there. That's the TPS thermal simulator, which is basically just a big oven we hang above the spacecraft to make sure that it's seeing the right temperatures that the TPS will impose onto the spacecraft at closest approach. We actually run the spacecraft in this test. So Nikki mentioned that there's a lot of autonomy and a lot of innovation that went into just making sure that this whole thing is going to work. And so while we're actually thermal cycling it, which is what we do in that chamber, we go hot and cold and hot and cold, they're also running all that software and all that autonomy to make sure everything is checked out and working. So that's actually where we are today with the spacecraft. It's sitting in that chamber. It's about halfway through its test cycles. We're still running the spacecraft, checking it all out. And so we'll leave the spacecraft for a moment, and I'm going to talk a little bit about the heat shield, which me and my team have been working on for a very long time, as I mentioned. So the heat shield, in addition to the innovations of the solar array and the cooling system, which I already mentioned, the heat shield is obviously an important innovation to making this mission actually happen after so long. So the front side of the heat shield is about 2,500 degrees Fahrenheit, and the back side is about 600 degrees Fahrenheit. And the bus is a little bit above room temperature, what you're sitting in right now. Nikki said we call it an 8-foot frisbee. So it's about 8 feet in diameter, it's 4.5 inches thick, and 160 pounds. So pretty lightweight, pretty small, really. Packs a punch, though. The construction is actually quite simple, but it just took a long time to figure out exactly how to do it. It's a sandwich panel, so it's a lot like honeycomb panel you find in your in a spacecraft, on the spacecraft bus that I showed, or on an airliner. You see a lot of honeycomb panels, where you have 2 face sheets with a core all bonded together for structural reasons. So in this case, this sandwich panel has 2 face sheets which are a carbon composite. That carbon composite is basically like the graphite epoxy you might find in your golf clubs or in your tennis racket, but it's just been superheated so it can actually withstand the sun. Inside you have a carbon foam, which again is just like a foam, but it's actually made of carbon. Carbon is a really great material at high temperatures when you're not here on Earth. Here on Earth we have oxygen, and carbon and oxygen don't play nicely here on Earth. They actually alight. That's how you have combustion. But in space we don't have that problem. So carbon is actually a great material for high temperature applications, and you find it in jet engine brakes and that sort of thing where you do have high temperature situations. Also re-entry vehicles, that sort of thing, that's where you find carbon. So one of the critical innovations of how to pull this all together was actually figuring out how to bond all of that together and actually have it survive. As you can imagine, you have all these components that work, but not only they need to be all able to function at the sun themselves, it needs to be as a system working together. So one of the critical innovations was figuring out how to bond it together. So let's take a look at what that bond looks like. So the main heat shield is built at a place called Carbon Advanced Technologies, and here you can see them actually bonding these face sheets to the foam. This is the foam, and it's got the carbon bonding material, and it's being flipped over and actually then bonded to the face sheet. Once you come down and you mate those 2 surfaces, they go through processing, and once we've done that once, we do it again on the other side. It's a pretty exciting time when we're actually doing the bonding process. So then we have a heat shield, and it's all together, and it's ready to go through its environmental test program. Here is the flight heat shield actually going into thermal testing at Goddard. You can notice it's actually the exact same chamber. It went in before the spacecraft, so even though it's in a different order here, it actually went in a few weeks before. So it went through vibration testing just like the spacecraft, and now it's coming in for its own thermal testing. We mimic exactly what the interfaces are going to be. You can see that there's a truss here, or the metallic structure below, and we actually hook it up exactly like it's going to be on the spacecraft. We have the interfaces, which are very small, so we reduce the amount of conduction down through the rest of the spacecraft, and then we actually build it up so that it can go through thermal testing. Here's a nice shot also of the front surface. So the front surface has a white coating on it that was also developed specially for this mission in conjunction with the Johns Hopkins Whiting School and the Johns Hopkins Applied Physics Lab. We developed the actual coating that went on, and it's plasma sprayed on the front surface, which is basically you superheat, you plasmatize the particles, and then you shoot them at the front surface. It's a method that's actually often used in turbine blade engines, other hot methods, but the coating itself was developed particularly for this mission. You can also get a really nice shot of the back side of the heat shield here. Another complicated thing that had to be figured out was how to actually lay up that back face sheet. That's all one piece, but also have those features to actually be able to connect and have it work with the rest of the spacecraft. So the last thing that we actually do after we've buttoned everything up and we've gone through testing and this testing has been complete, we actually put it on the spacecraft. So right now, as I mentioned, the heat shield is not on the spacecraft, but it was on the spacecraft for a quick fit check not that long ago. So here is the lift where we actually put it on the spacecraft. This was a very exciting day. It was the first time that it got its crown after so long. And we'll hold here. So this is from a couple of months ago, but this is what it's going to look like right before launch at the Cape. And I really like this shot because you can see all of those components, all those innovations that make this mission possible coming together on this spacecraft. And she's ready for her journey. So I'm going to kick it back to Nikki.
Thank you, Betsy. That was a great behind-the-scenes view of how you put together a spacecraft, and isn't she pretty? Yes. So where we are today, as Betsy said, the spacecraft is going through its final environmental testing at the NASA's Goddard Space Flight Center, and at the end of this month, we will bag her up and fly her down to the Kennedy Space Center area, where she'll go through her very final testing, get all the fuel loaded on, have her crown put on, as Betsy so nicely said, and then the next stop for us is atop of the Delta IV Heavy. Now, one thing, I'm not sure if you can picture this, but we're a very, very small spacecraft. We're about 1 meter in diameter and only about 3.4 meters tall. A Delta IV Heavy is enormous. We look like a hood ornament on the top of this rocket. We are tiny, but again, we need this huge kick to be able to achieve the speeds and to lose all of this momentum. And so that's kind of the next stop for us, but I just wanted to sort of tie a bow on the presentation by going back a little bit into history, because just a few months ago, Gene Parker visited us just after his 90th birthday at the Applied Physics Lab, where we were having a science meeting. And I got the great honor of actually introducing him, taking him to the spacecraft, and saying, "Parker, meet Parker." And so we have a nice shot here of Gene seeing the spacecraft. And unfortunately, you can't hear the sound. But one thing he comments on is he says how happy and like how excited the whole team that was in the clean room was. And I make the comment, unfortunately you didn't hear it, but I said, yes, look at all these happy smiling faces. And it is true. And if you haven't kind of got the impression that Betsy and I are really excited about this mission, you should see the thousands of people that work on this mission. And it isn't just the thousands of us who are working on the current version. It's the thousands and thousands and thousands of scientists and engineers who've poured their heart and soul into this mission over the last 60 years. And so we're all very excited. This mission is flying for all of us. And you can get excited too. You can join us on the journey. You can actually put your name on the spacecraft. If you go to go.nasa.gov/hot-ticket, you can enter your credentials for the hottest ticket this summer, and you can fly with us on the spacecraft, and together we will touch the sun. Thank you. And we are happy to do Q&A. They told us to finish well before, so you could ask questions. And I'm a little nervous to say you can ask me anything, but go ahead.
All right. Thanks, guys. So that was a great talk. So if you guys have any questions, there's a microphone there, so go ahead and please feel free to line up, and we'll take questions for the next few minutes.
Sure.
Hi. First of all, thank you for your great inspiration and your story. And sorry if this is a very stupid question, but here it goes. As you understood well, one of the challenges we have with the solar winds is the magnetic force and the impact of that on technology on Earth, right?
Yes.
And the thing I'm puzzled about is being in the wind, how is Parker going to manage the magnetic force in its own operating system during the flight?
Through a lot of early modeling and a lot of early estimating, and obviously, it's kind of the old you measure twice and cut once. We really overestimate what the worst conditions are going to be and make sure that she will be fine. I mean, it's extremely dusty where we're going, so we have to worry about dust impacts. So lots and lots of radiation, and clearly we're going to the biggest radiation source in the solar system. As you say, there's a lot of pressure. If you get it wrong, the spacecraft will flip around. And so it's really just over-designing for the worst possible case that we can envisage seeing.
And this is for the magnetic force as well?
Yes, for everything, for the pressure, for any changes in the center of gravity, center of pressure, anything that can happen, she's ready to correct for that.
Cool. Okay, thank you.
Okay, thank you.
Hi. I'm sorry. I'm really. This is tall. I'm sorry if my question is too simple too, but what kind of data do you want to collect in this mission? What are the mysteries that you want to solve?
Great, thank you, because I probably missed that out in my talk, so thank you very much for asking the question, and I didn't pay her beforehand. The mysteries, there are two main mysteries that we want to solve, and the first one is, why is the corona hotter than the surface of the sun? There are many theories, there are many things. Gene Parker, in fact, in the mid-70s, has his own theory that he published on why it happens. But people have estimates, people have guesses, but until you actually go up and really sample it, we can't answer that question. And the second mystery is what causes this material to get so energized and to actually form a solar wind? We're going into the birthplace of the solar wind. And so the measurements we need to take, we have done absolutely amazing advances using images and using spacecraft that are closer to the Earth, maybe out around the orbit of Mercury, the messenger spacecraft, for one example. And you can put those things together, but you can only find out so much with those data. At some point, you actually have to go up and visit. If you look out the window and you see the sun is shining, you'd have no idea how hot it is out there, you just know the sun is shining. So you have to go and really experience the environment. And so that's what we're going to do. For the first time, we're going to go in and make in situ measurements, make measurements of everything in the corona. And so the second part of your question was what measurements? So we will be measuring all of the particles that are there. We'll be measuring the electrons, the protons, all of the ions that are in there at all different energies. And so we can stack up exactly what's happening, different populations, different kind of species even, and then what is causing this huge flow. We obviously need to measure the magnetic fields. The sun is a huge magnetic star. The solar wind carries the field with it. How does that happen? How do you get the energy into that magnetic field that comes into the solar wind? We measure the electric fields and we measure all the waves. So if you think about as the particles are moving, they kind of let out little signatures. You can think of it as a sound wave, but it's really a light wave that comes out with the particles. And we're measuring all of those waves, in addition to taking the images of the solar wind as we go in. And so that's a long answer to a very good question.
Thank you very much. And I'm very pleased that 2 women are there. Thank you.
Thank you. There's lots of guys working hard at home too, yeah.
and more women too.
And lots more
there are
women.
lots of
Loads
men and
of
women
us.
who are
We're
doing
just
great.
2 of many
people. Exactly.
Yeah.
Hi. First of all, I really enjoyed your presentation. It was fantastic. And I was curious, when is the projected date for launch, and how long will Parker be in orbit collecting all of the information?
That's a great question too. So our launch window it opens July 31st of this year. We have a 20-day launch window. Now you may think, why the sun is there every day. Why can't you go to the sun any day? But you'll notice that I said our first stop was the planet Venus, and so our launch window is governed by when Venus is in the right place for us to be able to do that, that flyby. It will take us just 3 months, so 6 weeks to Venus, 6 weeks to the corona, so just 3 months for our first closest approach. We will repeat that with another 6 Venus flybys, 24 orbits in total. It's 6 years and 11 months for us to do our full mission. After about 6 years, we are at our closest approach, and we're within that 4 centimeter or, the red zone. We're at the 4-yard line on the football field, knocking on the door for a touchdown. That's what we're doing after about 6 years. So it's a long mission. It's fun because we do get data very quickly. We don't have a long cruise phase. We don't have the agony of New Horizons going to Pluto. We actually get data in 3 months. But on the other hand, we have to wait 7 years to get to where we really, really, really want to be. But we'll get great stuff all the way in.
Which is, 7 years, the heat shield, that's the money moment. So me and my team are waiting anxiously.
Yeah, there's no pressure on Betsy at all. Hopes and dreams of thousands and thousands of people.
That's why I have a great team. That's why I have a great team.
Yes.
Thank you. Knowing that you've been working on this for over a decade, when did you guys lock down your designs?
So that's a great question too. So we'll say we were confirmed in 2013, 2014, in that sort of end of 13 timeframe. And that's when we really said no more changes. Now, have we changed anything and tweaked things? Of course. But, you do. You find you're not going to say, oh, we found a better way to do it. No, no, no. You're going to do it. But the big design changes were done, the big design sort of freeze was done in late 2013.
So I mentioned that integration and test started in July of 2016. So obviously there's a portion of time between when you lock down the engineering design and you start building things so that they're ready to actually put on the spacecraft. So actually the very first, we've built a total of 4 TPSs, actually, not just one. You don't want to do just one. And so the very first one, which we built, was in 2013 to prove out the technology. It looks surprisingly similar to the flight one. There are some differences. I, of course, know all the differences, but they're very, very similar to one another. And that's true across all of the engineering. As you kind of lock down that design and you start actually building flight hardware, there's a long time that it takes just to test that flight hardware and then put it actually on a spacecraft. So these are long time periods. So 2013 is about when everything locked down.
Right. Yes?
Hi, thanks a lot for sharing all this information with us and all this excitement too. I'd like to ask you if you could repeat, please, the temperatures the probe is going to meet there, the distance is going to be from the sun, and the speed per second it's going to reach the right spot.
So I'll talk about the temperatures, and then I'll let Nikki talk about the other two, because she's got those memorized. So the front side of the heat shield is going to be at about 2,500 degrees Fahrenheit. The back side, that 4.5 inches later, is at about 600 degrees Fahrenheit. And then the spacecraft bus, where almost everything is sitting, which we talked about, is just over room temperature at about 85 degrees Fahrenheit.
Okay, so our maximum speed is 430,000 miles an hour, or about 118, 119 miles a second. So New York to Tokyo in under a minute. Our closest approach is 3.9 million miles from the solar surface. And as you all know, the Earth and the Sun are 93 million miles. Whoa, that was a quick journey. 93 million miles apart. And so that's our closest, hottest, fastest. We're not competitive at all. Yeah.
Hi. Did you say that the mission total plan was for 7 years?
Yes, the prime mission is 6 years and 11 months. Once we get to the end of that time period, we still have fuel. The final orbit is completely stable. I always get asked if we're going to crash into the sun.
Yeah, that's what I was going to ask. Is there a coup de grace?
The last one is completely stable, so we can keep going while we have fuel and money.
My money's that you guys will get 9, 10 years at least.
I would love to. Yes, job security, 9, 10 years would be great. Yes.
Hi. So it's very interesting to hear about all the information we're going to get from this mission. are there technological possibilities as well that we might learn about? It's as far as so we're very curious about all this data, but is there any applications to technology that we might get from it?
So I can answer that from the science point of view, and I'll let Betsy comment on the future applications of some of the stuff she works on. The big technology advancement really from the science point of view is, I talked about space weather, and I talked about the need for accurate modeling of what is happening on the sun and how it's going to impact the Earth. A recent National Academy study said that if we had an event of the size of the Carrington event I talked about in 1859, if we had that today and we had no protection, the US alone, it would cost about $3 trillion of damage, and we could be without power for up to a year. And so, you know, Solar Probe is going into the last region. I am biased, and I would say the most important region, but it is going into really the last region of the solar system to be explored. And it's that missing piece in the model of the sun to the Earth. And so it's like the last piece of the puzzle when you want to put together what's happening. That's where all the excitement happens. That's where the magic happens. That's where the solar wind is born. And until you can model, I mean, as soon as we know what physical processes are causing that solar wind to happen, we can put that in the modeling, and we can do just dramatically better job of predicting what is going to hit the Earth. And so from my slightly small scientific technology piece, that is my thing I'm looking forward to, and I'll let Betsy give you probably a much more fun answer.
So, I mean, just to highlight what Nikki's saying, so part of this in terms of imagination is we're going there to rewrite science, right? We're going to rewrite the science textbooks. That's the whole point. And we don't quite know. Lots of people have a lot of different theories, but until we go, we're not even going to know. There's an imagination, and so exciting that 10, 15 years from now, people will be learning different things about the sun because of this mission. And so it'll change the way we look at it. From a technology point of view, you know, I talked about the advances in heat shield technology, and that is applicable to reentry vehicles and hypersonics and things that get hot and need to be hot and function. The solar cell technology, the cooling system technology, and then also the autonomy. Nikki mentioned that this spacecraft has to basically run itself. It's near the sun, can't talk to it. If there was a problem, it needs to fix itself. So the work that's just gone into that fault management, that autonomy, has just changed the way that we actually can approach that kind of problem on a spacecraft. There is no joystick here, and there's so many people and innovations just behind that work.
And just to give you an idea of how enthusiastic our fault management team is, the moment these guys stop playing with the spacecraft in integration and test, they swoop in and start testing the fault management. It's like there's a moment they will come and take it. Yes.
Hi. So you actually started to talk a little bit about some of the expectations from the learning side. So I was wondering, you know, some of the other programs like the Mars rover, there's a lot of information that was coming to the general public to get us excited about what was being done, and also specifically in classrooms to get children excited from an early age. Can you speak a little bit about how we're going to continue to learn about what you're doing and how we can continue to be excited about it?
Yeah, so I mean, we you know, obviously we have a website. All NASA data are public, so you can, you know, follow along and take the data. Now, obviously, you know, second-order plasma polynomials, maybe not your cup of tea, but you know, we will be doing a lot of translating that data into, you know, I work with school kids all the time. I have young kids, and so I'm always in the schoolroom, and it's amazing how excited they get about this stuff. And so working with teachers, working with educators, working a lot with museums. So actually, a couple of weeks, I'm doing a training for people that run museum centers so they can better share the material. We don't have a full education program with the mission. NASA's gone a slightly different way with how they handle that now. But we have a lot of communications and engagement. And so, you know, our goal is to make sure that people are understanding. As Betsy, it was a beautiful quote that Betsy had, you know, we're really rewriting textbooks, and there's no point rewriting the textbooks if only 2 people read them. And so, you know, we really are committed, venues like this, to, you know, I hope we'll come back again and tell you what the wonderful science results we have. But really just engaging the public, engaging the excitement, send your name to the sun, you know, and join us on the mission. It really is, it's such a historic it's something I think that captures the hearts and minds of people because it really is such a tremendous feat for what we're doing. And so, you know, follow us. You can follow us on Twitter, you can follow us on Facebook, you can Instagram, we do everything. So, you know, that's kind of how we're getting a lot of our message out. But it is very important to me personally that we get our science into the public and they, you know, they can appreciate what we're doing. It's your taxpayer money.
Thank you.
So the Twitter handle for Parker Solar Probe is @SolarProbe.
No, it's Parker Sun Probe.
Parker Sun Probe.
For Solar Probe. Facebook is Parker Solar Probe.
And then Johns Hopkins Applied Physics Lab is @JHU APL. And
Correct.
both will be talking all about this mission.
Yep. And she will tweet on orbit too. We hope. Yes.
Hello. I have a pretty naive question. I've always wondered how spacecraft stay the position they should be. Do they have external propulsion systems like Wall-E in space? They will,
Yep.
you know, use fire extinguishers to stay where
Yeah.
they should be?
So, yes, so spacecraft, depending on the mission, but generally have thrusters all around them. And you think about it, and so there are different types of thrusters, but one of them is like a 1-pound thruster. And you're like, wow, that seems really small. But you're in space. It only takes a little bit to actually go. Some of the early pictures that kind of flew by, but if you look at the talk later, there's a like big pink ball in the middle of the spacecraft. That's actually the propulsion tank. It's covered in pink because that's a protective foam. It's a pretty thin-walled cavity, and so they want to protect it while all these other things are coming in. The propulsion system is actually usually one of the very first things get put on a spacecraft because it's kind of in the middle and it's running all over the place. And so then there are thrusters throughout it. And one of the things that the autonomy will do is basically fire those thrusters looking at how the solar pressure is happening, how the spacecraft is flying, and make sure that that heat shield is always pointed towards the sun.
So that probably applies to almost all the spacecraft that go.
Yeah, so that's very similar to all the spacecraft. It depends on, there are lots of different types of spacecraft, there are lots of different types of propulsion systems, but generally on a medium-sized spacecraft, there's an active propulsion system that's actually inside there. You just don't see it because it's hidden behind all of those blankets.
Cool. Thank you. Just last question. How real time is the data going to be? I'm a designer, I really enjoy data visualization. So I'm curious what kind of preparation is done to visualize that data that is going to come in real time. I know Mars is like a 7-minute or 20 minutes delay. So how long is that to the sun? And what are we going to do to make it more useful for the scientists, to make it look interesting to the public? To make the data meaningful.
So we won't get anything back in real time. We're what we call a store and dump mission. I mentioned how fast we're moving. Sometimes we have a large glowing body called the sun between us and the spacecraft, and it just literally makes it impossible for us to be able to close the link. And so what we do is that anytime we can see the spacecraft, we downlink data. There are some orbits where we actually do a full orbit and we're on to the next one before we can pull down the data just because the sun is in the way. But it's typically 3 months and we'll see our data, sometimes quicker than that, sometimes agonizingly longer, but usually about 3 months is a good average. For data visualization, each of the instrument teams will get their data and they're working on visualizations. We're also working, so at the Applied Physics Lab, we have a really nice tool called a HoloLens. And so one of the things we did with it was we actually did a full augmented reality version of the spacecraft. And these guys used it a lot in testing how they were going to actually integrate the spacecraft. You know, where is my hand going to go? Where is my foot? Let's not knock into something. And so they actually, you know, did a lot with that. But we also have a version that is flying along with Solar Probe, and we're going to do data visualization in this kind of augmented reality version that will allow us to see the spikes and see what the data are doing to better help us as scientists, never mind, you know, being able to bring it to the general public. It's going to be confusing as heck to the scientists because we're going somewhere we've never been with, you know, things moving all over the place and a spacecraft moving incredibly fast. And so we'll actually be, at APL, we'll be doing the data visualization using this HoloLens tool. So you'll actually kind of be able to ride along with the spacecraft and maybe you'll see the solar wind rearing up in front of you or something. But that's one of the tools we're doing. Each of the instrument teams have their own data visualization. We're also working with the Jet Propulsion Lab to do data visualization too, because it really is important to not just have wiggly lines, because I may get excited about wiggly lines, but not everybody else does.
And polynomials.
And
Not
polynomials,
not just wiggly lines.
coefficients, yeah.
And we have time for like one more question.
Okay, then I'm the last question. You mentioned the solar eclipse last August. I wondered what new insights you learned, and if that changed, or did it cause any changes in the design of the probe?
We didn't. I wouldn't say we learned anything from this particular eclipse that would change our design. Also, it's a little bit too late for us to change our design. It was my first eclipse, so the thing I learned is, wow, the corona is pretty. I've never seen it before with my naked eye. So, but there were NASA had a lot of experiments. They did a lot of ballooning experiments and things that they had the Sophia planes flying. There's an awful lot of data. They're in the process of kind of unpacking all that data, because you can imagine it was a big citizen science project where everybody took stuff and they're putting it together and kind of unpacking it. So as far as solar probe is concerned, other than saying, wow, the spacecraft's going to be right there when I was looking at the eclipse, nothing big for the change of the design. I'm pleased to say, I think I'd be terrified actually if we found out something during that eclipse that needed us to change the mission design. We wouldn't be launching this year. But anyway, thank you so much for coming on behalf of Betsy and I and the thousands of people. And don't forget to sign up, send your name to the sun, go.nasa.gov/hot ticket.
And follow us on social media.
Follow us on social media.